In science, chaos and order are two opposing ideas. Chaos means unpredictability, a system where small changes at the start can lead to huge differences in the outcome. Order, on the other hand, is predictable and regular. Strange Non-Chaotic Attractors, SNAs, sit between these two extremes. SNAs are systems that behave in a complex way like chaos but remain stable and predictable, unlike truly chaotic systems. They are special because they combine the fractal, repeating, detailed patterns of chaos with the stability of ordered systems. Think of a pendulum being pushed in a unique way by two forces that don't sync up, like two rhythms that don't align. Over time, the pendulum follows a complex but predictable pattern, a hallmark of an SNA. Imagine walking along a forest path. The twists and turns seem random, like chaos, but if you follow it carefully, you notice it repeats in a consistent pattern, like order. An attractor is where a system naturally settles over time. For example, if you swing a pendulum and let it slow down, it eventually stops at the lowest point. This is its attractor. Chaotic attractors. They show complex, repeating patterns, but are extremely sensitive to small changes. For example, weather systems are chaotic. Tiny changes in temperature can drastically alter the forecast. Non-chaotic attractors. These are simple and predictable, like the steady ticking of a clock. Strange Non-Chaotic Attractors, SNAs. SNAs look complex like chaotic attractors, but they are not sensitive to small changes, meaning their patterns are stable over time. A pendulum influenced by two forces with mismatched rhythms can create an SNA. The motion is intricate, but it follows a predictable and stable path. This is like climbing a spiral staircase. It looks complicated, with steps twisting and turning unpredictably, but the staircase consistently leads upward or downward, like an SNA balancing complexity and order. Fractals are patterns that repeat at smaller and smaller scales, like a tree where every branch looks like a smaller version of the whole. SNAs inherit this fractal quality from chaotic systems, but unlike chaotic systems, SNAs remain predictable over time. This means that while their structure is detailed and intricate, they don't spiral out of control. The shape of an SNA might look like a jagged coastline. If you zoom in, the jaggedness repeats itself in smaller and smaller scales, showing fractal behavior. Think of a snowflake. Each branch is detailed and complex, but the overall shape follows a consistent pattern, much like SNAs that are intricate but predictable. Quasi-periodic forces are the key to creating SNAs. These forces come from systems driven by rhythms that never repeat exactly, like two clocks ticking at speeds that are out of sync. This mismatch creates patterns that are aperiodic, never repeating exactly, but still deterministic, predictable. SNAs emerge when such quasi-periodic forces combine with a system's natural dynamics, resulting in complex yet stable behavior. Celestial mechanics provides a good example. The orbits of moons around a planet can follow quasi-periodic forces, as their motion is influenced by multiple gravitational pulls with mismatched rhythms. Imagine two musicians playing tunes at different tempos that don't align perfectly. Their overlapping sounds create a rich and intricate harmony, much like quasi-periodic forces shaping SNAs. SNAs are studied using mathematical models that describe how systems respond to quasi-periodic forces. These models show how systems can transition into SNA behavior as certain conditions, like the strength or frequency of forcing, are adjusted. The mathematics reveals how SNAs inherit fractal structures while avoiding chaotic unpredictability. Consider a vibrating string being plucked while another force pulls at it irregularly. The resulting motion is neither completely random nor perfectly simple, but it matches the structure of an SNA. This is like a tightrope walker balancing with two competing winds blowing at different speeds. The walker's path may appear complex, but it is ultimately stable and predictable. Scientists have observed SNAs in real-life experiments across different fields. Electronics, oscillators driven by two mismatched frequencies can form SNAs. Mechanics. Systems like vibrating metal plates show SNA behavior when influenced by dual-frequency forces. Astrophysics. Planetary systems with quasi-periodic orbits can exhibit SNAs. In an experiment with electrical circuits, researchers applied two signals with mismatched rhythms to an oscillator. The circuit's response formed an SNA, displaying a stable but intricate pattern. This is like ripples on a pond from two stones dropped at non-repeating intervals. The overlapping ripples form complex but stable patterns, just like SNAs. Applications of strange non-chaotic attractors. SNAs have practical uses because they combine complexity and stability. Signal processing. SNAs can create complex signals that are hard to predict but easy to reproduce, which is useful for encryption. Astrodynamics. Understanding SNAs helps scientists predict the complex orbits of asteroids influenced by multiple gravitational forces. Climate modeling. SNAs can model non-repeating patterns in ocean currents or weather systems. Challenges in studying strange non-chaotic attractors. Studying SNAs is difficult because they are in between chaos and order. Identifying SNAs. Distinguishing SNAs from chaotic behavior requires precise tools to measure their fractal nature and stability. Modeling complexity. Quasi-periodic forces introduce mathematical behaviors that are challenging to simulate accurately. Reproducing in experiments. Setting up the right conditions to observe SNAs in the lab demands high precision and control. Persistent mysteries and future directions. Despite progress, strange non-chaotic attractors remain mysterious. Scientists still don't fully understand how systems transition into SNAs. The exact steps leading to SNAs are not clear. Whether SNAs exist in quantum systems, researchers are exploring if SNAs can appear in systems governed by quantum mechanics. Potential technological uses. SNAs could lead to breakthroughs in encryption and signal processing. Some researchers believe that quantum systems with quasi-periodic potentials might display SNA-like behavior, offering a new way to study quantum and classical physics connections. This is like studying the boundary between a calm lake and a turbulent waterfall. The transition reveals both beauty and complexity, much like SNAs. Conclusion: a bridge between chaos and order. Strange non-chaotic attractors are a fascinating middle ground between chaos and order. They blend the intricate patterns of chaos with the stability of order, offering new ways to understand the behavior of complex systems. SNAs challenge traditional ideas about predictability and stability, making them important for fields ranging from astrophysics to secure communications.